Okay, so I have uploaded this paper. This is the last year end exam paper, and also I have uploaded the tech DSP paper. Okay, so you can do the questions in both paper. Okay, so your paper is very much equal to this paper. Okay, this one. Okay. Uh, so I think same questions are also repeated as I can see. Okay. Uh, so if you could do this paper um, with understanding, okay. If you could do this paper with these questions with understanding, okay. So maybe you can get a good score. You can get a good marks for the this year semester also. Okay. And 8 point this sorry this F50 questions are not included in this year. Okay, so you no need to go through this F50 algorithms. Okay, hallucination in time, so hallucination in frequency algorithm you no need to go. Okay, uh, so other than that I think all discussed topics will be there. Okay. 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 Actually, I don't hope to do much examples. Okay. I think enough examples are discussed, and also the recorded sessions are uploaded so that you can find the examples there. Okay. Uh, so first of all, your paper will be having 4 questions. Okay. 4 questions. 4 questions. Okay. So you will be having 4 questions. Okay. 4 questions. Each question has 25 marks. Okay. So one question have 25 marks. One question has 25 marks. Okay. So first question based on sampling actually. Sampling. Second question based on Fourier transform. Fourier transform. Okay. Fourier transform. So in Fourier transform, actually only Fourier transform will be there. Okay. No Fourier series. Fourier series. Fourier series representation not there. Fourier series representation maybe not there. Okay. Fourier transform. This is for aperiodic signal. Aperiodic signal. Okay. And third one, you will have discrete Fourier transform. Discrete Fourier transform. Discrete Fourier transform. And Z transform. Okay. Z transform. So for the Z transform, around 10 marks will be there. And discrete Fourier transform, 15 marks will be there. Okay. So 10 to 15, 10 and 15. So that we will get 25 marks. Okay. And fourth question will be based on, discrete, FIR filter design. FIR filter design. Filter design. Filter design. Actually, this time also that is the only thing we can do windowing techniques. Okay, we are using windowing techniques. to design the FIR filter. Okay. So these are the four questions. Okay. From these topics, we will get four questions. Okay. To your exam paper. Okay. I think it is same as previous one. Okay. So this is actually based on sampling. Okay. So this question is based on sampling. Sorry, here actually Fourier transform part is also there. Okay. But in this year, okay, question will be one will be depend on sampling. Okay. Totally sampling. Okay. So I think if you put these questions with understanding, you can do the question. Okay. You can do the question in the exam. I will do some question here. Okay. I will just give you a guide. Okay. I'm not going to go in the questions. Okay. And yeah, question 2 is based on Fourier transform. Okay. Actually, you will be having the Fourier transform from here to here, Fourier transform. I think structure is somewhat different from the previous one. Okay. In this year, your question will be your questions were uh, lined in this way. Okay. Your question is called organized in this way. Okay. But you can see that in previous paper, some questions, for example, in question 1 is not only the sampling, but there are some Fourier transform part is also there. Okay. And here you can see that question 2, Fourier transform is there and discrete Fourier transform is there. These are two things. Okay. Fourier transform is different from a discrete Fourier transform. I will tell it later. Okay. So maybe you can remember. Okay. So here in this side, in this here, question 2 will be totally depend on Fourier transform, and question 3 will be on discrete Fourier transform plus Z transform. Okay. And here the question 3 is totally depend on Z transform. Okay. But this time DFT plus Z transform will be there. Actually, uh, if we see generally, I think this year paper is more easy and more simple than this one. Okay. I think most questions are repeating as I can see. Okay. So if you could do these questions, I think you will be able to do. Okay. The paper very well. No problem. Okay. And question 4 will be on filter design, actually filter design and systems also. Okay. Actually that is based on system design and analysis. Okay. So the systems we used as a system, we choose the filter. So it will be based on the filter design. Okay. So it is in this way. The paper is organized in that. Okay. And we will see some details. I will give you a just a recap. Okay. I will give you a just recap. Okay. So I think it is better when you are doing this question, you better use the uh, better use your reference book. Okay. So so that you can get understanding actually. Okay. So you can read the related things and you can get understanding, uh, deep understanding on those questions. Okay. Okay. So first question, as I told you, it is based on sampling. Okay. Based on sampling. So we have learned the sampling. Actually, we have learned the sampling and reconstruction, but the question is depend on only sampling, okay? Not the reconstruction. Um, Okay. Actually, sampling is the first step of analog to digital conversion. Maybe you can remember it. Okay. And I think this equation maybe you can remember. Okay. This is how we can represent the sample signal. Okay. Uh, so using uniform sampling, impulse train sampling. Okay. This is uniform sampling, no impulse train sampling. Okay. And this is the sampling frequency, that is the sample per 1 second, and this is the sampling time. Okay. So this relationship also we have learned. These are basic relationship. Okay. So actually in the sampling question, you have to use these basic equations only. Okay. And this is how time is related with the this n sample. Okay. Uh, So this is the basic idea of sampling, okay, impulse sampling, okay. So this switch is on using an impulse, okay. So between two impulse, the sampling time is there, okay. So if you know the sampling time, you can get the sample from this signal easily, okay. Uh, and also we have learned this one also, okay. So maybe you can remember that if if a sinusoidal signal is sampled, A cos 25 fp plus 5 is a continuous time signal. And if we sample this signal using sampling frequency f, we can write the sample signal. Sample signal is a discrete time signal. So you can write it as cos 25, this frequency divided by sampling frequency. Instead of this t, you will have n, and the same phase is there. Okay. So this is how we can represent a sampled signal. Okay. So this will be f divided by fs. This is we referred as normalized frequency. Okay. So normalized frequency here defined as f. Okay. So maybe you can remember that this normalized frequency should be in this range. Okay. It should be minus half and plus half. If it is exceeding, okay, exceeding, uh, if is exceeding this range, that means there is a fundamental frequency, discrete frequency will be there related to this within this range. Okay. So that is defined using using the equation. Maybe you can remember that equation. The higher frequency, okay, it is normally referred as fk. So that is equal to fundamental frequency. So this frequency will be range minus half and plus half within the range plus k. Okay. So this k will be integer 0, 1, 2, 3. Okay. So if you have any frequency uh, beyond this limits, okay, so there is always a frequency within this half, plus half and minus half. Okay. In other way, for the frequencies within plus and minus half, there will be uh, identical frequencies. Okay. Higher frequencies may be there. Okay. So these frequencies are referred as Eliasing frequency. These are the Eliasing frequency. Okay. So if you need to remove this Eliasing frequency, your fundamental frequency should be within minus half and plus half. For that one, this sampling frequency, you need to select at least twice of the signal frequency f. Okay, so this is named as Nyquist theorem. Okay, Nyquist theorem. These are the basic things we have learned. Okay, and I will go to example here. Okay, okay, these are actually there are some basic questions, okay? So I think you can do this by yourself. You need to compute the fundamental period uh, of this discrete time signal. So, so you know that 2, 5 normalized frequency n. Okay, so this f is the normalized frequency. So the fundamental frequency you can get as 1 over f. Okay, using this equation, you can directly calculate these values. Okay, okay. And also, I think this is somewhat important, I hope. Okay. Uh, can anyone tell me, is this signal periodic signal or not? Is this periodic or not? Is this periodic or not? Can anyone tell me? Yes, it is no. How? Maybe no. Yeah, I hope it is not. No. How can you say that? How can you say that this is a periodic or not? Yes. Okay. Your question is somewhat correct. Okay. Somewhat correct. Okay. Uh, actually, this all. So just try by yourself to do this question also. So this one will be an interesting question. Okay. Maybe you have to use this knowledge for the exam papers also. Okay. Uh, so I will give you some clues. Okay. For example, maybe can you remember that if we have a signal, continuous time signal like this, cos 2, 5 f1t plus, this is some value, a2 sine 2, 5 f2t. Okay. So if I ask you to find the period, and if I ask you to verify this is periodic, and if I ask you to find the period, can you remember what is the procedure to calculate the period? Okay. So I will, so this is a continuous time signal. Okay. So I will tell you, it is somewhat like this. Okay. So you can choose this signal as x1, this signal as x2, this period is t1, this period is t2. Okay. So you can calculate the period of x1, that is t1. What is the period? 1 over f1. No? And t2, the period is 1 over f2. Okay. Uh, and if you want to verify this is a periodic signal, okay, so you need to get the ratio of this t1 and t2. Okay. So you will have f2 into f1. Okay. f2 into f1 in this way. Okay. Uh, then you need to simplify this as much as possible, but as a ratio, as a integer. Okay. This, there should be an integer and here should be an integer. Okay. So you are not getting the decimal value. Okay. Then let's say that once you uh, uh, simplify this k1 into k2, this kind of question, integers you will get, then the total t is equal to t1 k1, t1 k2, t2 k1. Okay. So in this way you will find the total frequency. Okay. The this composite signal period. Okay. This is the period of the composite signal. Okay. Uh, so if this k1 divided by k2, this ratio, okay, if this number is a rational number, this signal, this composite signal is periodic signal. If this is rational, it is periodic. And if it is not rational, it is not periodic. Okay. Why it is happening? Can anyone tell? If it is not rational, it will be not a periodic signal. Rational means it should be an integer, okay? It cannot be a decimal value. Rational value 5 is a irrational value. Root 2 is a irrational value, okay? And rational value means the number can be represented as a ratio. For example, 0.333 like this. This can be represented as a shared ratio 1/3. Okay, so this is a rational number, but 5 you cannot. Okay, so 5 normally defined as 2/5/7, but this is not exact value. Okay, this is approximation value. So if you get this value, okay, so you will have 3.14. Likewise, it is not ended. Okay, it is going. Okay, and for example, if you get 3.5, it is also a ratio because 35 divided by 10. You can write 3.5 like this. Okay, so it will be 7 into 2. So this will be a rational number. Okay. So why, if it is not rational number, why this is not periodic? That is my question. Actually, as the period, okay. So once you get the period, you will have the, as I can remember, you will have the greatest common divider. No? The greatest common divider මට මේ දෙක පැටලෙනවා හරි greatest common divide එකද නැත්නම් අර least මොකද ඒ කියන්නේ උඩාම පොදු ගුණාකාර මහා පොදු සාධකනේ මේක මහා පොදු සාධකය තමයි හොයන්නේ නේ greatest common divisor means the biggest number that biggest number from which this two value can be divided no the t1 t2 can be divided the biggest number using which this T1 and T2 can be divided. Both T1 and T2 can be divided without a remain. Okay, so that is the greatest common divider as I can remember. Okay, so you are yeah, greatest common divider. Okay, that is the greatest common divider. Okay, so if it is a rational, if it is not rational, actually there is no greatest common divider. Okay, there is no greatest common divider. So you can't get a value. You can't get a value. You can't select a value that T is equal to T1, K1 is equal to T2, K2. Okay. So once you select a value for this T, that value, using that value, this T1 also should be divided without a remain. And this T2 also should be able to divide without a remain. Okay. Yeah. Okay. So if it is not a rational value, you can't select, you can't get a value for this T. Okay, you can't get a value for this T. So this signal will not be periodic. If this is not rational, this signal will not be periodic. Okay, so that is a very important concept. Just remember it. Okay, just remember it because maybe you can see that. Okay, okay, you can see that these questions you need to answer based on that concept. Okay, for example, for example, if you consider this one, what is the period of this signal? What is the period of this signal? So that will be okay. So this is the so it is 5n. No? So normally it is 25fn. No, okay, 25fn. So if you consider this one cos 3, if you put 25 here, 5 divided by 25n. Okay, so this will be the normalized frequency for this signal. Okay, so this for this signal normalized frequency will be 5 divided by 25. This is the normalized frequency. So then what is the period? Normalized period, not normalized period, period. Period will be 1/f. That means 25 divided by 5. This is not a rational value. This is not a rational value because 5 is not rational. Okay, this is not rational value. So this signal not periodic. This signal not periodic. Okay. So it is not the uh, so you can see that the period will be, there is no common period. Okay, so this 2 5 can be any value, 3.143. So it can be any values, okay, within this range. Okay, so you can't calculate the exact period for this signal. So that the signal is not period. Okay, uh, and the same concept is there. So try to do this one also. Okay, so you can see that. Okay, for this signal, if you consider this signal 25n, 25n, 25 divided by n. This is the normalized frequency, f. Okay, 25n. This is the normalized frequency, n. 25k n, 25k divided by n. This is the normalized frequency, f. Okay, so if you consider the period, it will be n divided by 25k. Okay, so this should be the rational value. This should be the rational value. For that one, the k should be there. K should be, K should be able to make this statement ration. Okay. Uh, so in that way, uh, maybe you can try to prove this. Okay. The fundamental period of this signal. Okay. So try to do it by yourself. Okay. So I think sampling may be enough. Okay. Uh, and the second question will be based on Fourier analysis. Okay. Fourier analysis, but you will be having Fourier transform. Okay, Fourier transform, discrete Fourier transform for discrete time signal. Okay, so frequency analysis of discrete time signal, and this is for the periodic signal, discrete time periodic signal. Okay, so this part will not be there. Okay, so your mostly your questions will be depend on this one for that periodic signal. Okay, and this is the identity you need to use. Okay, you need to use, this is the identity. Okay, so this is how we represent, how we convert time domain signal into frequency domain. Okay, so if you given a sequence, you will be able to do this very easily. Okay, so this is not a much big one. Okay, so very easily you can do that. Okay, for example. Okay, so it is like this. Okay, so so this, there is a sequence. Okay, so this sequence. Okay, so here the sequence, you will have xn, you will have 1 1 1 like this. It is actually a finite sequence. Okay, so it is from, this is from minus m to plus m. Okay, and somewhere 0 will be there. Okay, so it is like this kind of sequence. Okay, so maybe very easily you can uh, show this. Okay, you are not asked to show this, but I think you will be able to see this. Okay, show this. What you need to do, you need to use the basic definition of Fourier transform. Okay. So that is xn e to the power minus j omega n sigma n from minus infinity to plus infinity. Okay, so if you apply this, okay, if you apply this, Okay, it is somewhat like this. Okay, so you can write x omega as if we started from minus m. Okay, xn is 1 e to the power minus j omega n. N is minus m, no? So it is uh, j omega m. Okay, plus again 1 e to the power. Now it will be maybe m minus 1. So minus m minus 1. Okay, minus m minus 1. So it will be j omega m minus 1 like this. You will get like this. Okay. And so zeroth value you will get 1 at the zeroth. Okay, you will get 1. Again, it is so again it is starting from plus 1. So it will be 1 e to the power minus j omega plus 1 e to the power minus 2 j omega. So on. Okay. So here also you will get, okay, before 1, you will get e to the power j omega plus e to the power minus 2j omega like this. Okay. So if you use the Euler formula, for example, you can write this as cos j omega m plus j sine j omega m. Okay. And final, you will get the minus value, no? Plus m. Okay. So you will get e to the power minus j omega m. Okay. So minus j omega m, you can write this as cos j omega m minus j sine j omega m. So you can see that sine value will be cancelled and only cos value will be there. So cos terms will be there. Okay. And it will be from 1 to m. No, this m will, so there will be terms from 1 to m. So you can write it as a addition. Okay, so easily you can show this. Okay, and uh, so x1 and x2 is given. X1 given as this sequence, and x2 given as this sequence. Okay. So if you apply the Fourier transform directly, very easily you can get these answers. Okay. So I'm not going to do it. Just apply the Fourier transform like this. Okay. So you need to expand this. That is the only thing you need to do. So very easily you can get this value and this value. Okay. So try this by yourself. Okay. And if you want to use this, actually I try to use this and try to get this value, I couldn't get. Okay. Maybe just try it by yourself. Okay. So maybe to show this equation, you have to use this terms. Okay. So without this terms also you can get by applying the Fourier transform directly to this sequence and this sequence. Okay. So that is very easy. You can get this value and this value. Okay. And maybe you can try whether you can get this answer from this one. Okay. I tried, but I couldn't actually. Okay. Okay. So that is based on question 2 actually, Fourier transform. Okay. So question 3 will be on discrete Fourier transform and Z transform. Okay. So so for the Z transform, actually, I think you need to know only the basic things. Okay. For example, so very easily you can find the Z transform of this kind of signals. Okay. So this is not much difficult. You have to use this identity and you have to expand this. Okay. So that is what you need to do. Okay. So I think you know how to do that. Okay. Then this kind of one also you can get. This is actually power series. You will get the power series. Okay. So uh, using this what is this called Maclaurin examples. Okay. Maclaurin expansion. Okay. So using this expansion, you can easily calculate this kind of questions, this kind of signals is a transform. Okay. Uh, okay. So for example, this is the Z transform of UN. Okay. And if you get the inverse Z transform, you will get the inverse one. Okay. So maybe you need to evaluate the inverse Z transform. Okay. But for evaluating inverse uh, inverse Z transform, you need to do a what is called uh, that integral, vector integral. Okay, but that is not easy. Okay, so maybe you will have to use a direct method. For example, if you know this, if you know the Fourier transform of UN is this one, and if you given this kind of one, maybe you can identify the inverse Fourier transform is UN. Okay, so using by exploring this expression, you can directly evaluate the is a transform. Okay, inverse is a transform. Okay, so that kind of questions will come to you. Okay, and sometime maybe maybe you have, for example, if you consider this one, the question. If you consider this one, okay, so you can actually, you can very easily show this, okay? You can very easily show this. If you see the books, you can see the examples, okay? For example, it is like this, okay? This example, okay? It is actually identical to this example, okay? So if you just see this example, this is not much difficult, okay? I think recordings also I have done this, okay? So you can directly find this one, okay? Uh, then so is a transform properties will not come to you. Okay, so you no need to worry about this one. If maybe if you could just try it, it will be okay. Okay, and for example, it is like this. Okay, for example, okay, so this is the Z transform. Okay, so this is the Z transform. Okay, and I have give a hint here. Okay, so this one, so you can see that if I get out, I will do this question, okay? Okay, so it is like this. So, so yz is given, that is 2z into 9, z5, z minus 5, z minus 4 in this way, okay? So this can be written like this, okay? So you can see that here you have two Z only. So maybe you can get the Z out here. Okay. So you can write Z into 9 as uh, uh, for example, if you can get one Z here, okay. So you will have Z minus 4, maybe Z minus 4. So you can see that that term is there. And if you consider another here, if you get another Z, okay, and it will be Z minus 5, Z minus 5, okay. So you can get, um, okay, you can, Yeah. Okay. So, okay. So this is, and here you will have z square, z minus 5, z minus 4, no? Okay. So maybe you can write this like this, no? You can write this as, because this is a plus here, okay? So by taking the common emitter, you can write like this, z 5, z minus 5, z minus 4, plus z, z minus 5, z5, z minus 5, z minus 4. In this way, no? Okay. So you can see that here z4 cancelled. And you can have here z4, and here z5 cancel. Here you will have z4. Okay. So you can write um, z9 as 1 over z minus 5 plus 1 over z minus 4. Okay. And here you will have z4 and z4. And here you can get this as 1 over z, 1 over z, 5, again 1 over z5. Okay, in this way. It is like this, okay? uh, so I will do it again, okay? So here actually you need to consider these things, okay? So we are given a LTI system. We are given a LTI system, okay? And you know that if you give an input, okay? If you give an input and if you have the impulse response and if you got the yn, so you know that yn uh, can be written as xn into xn convol hn. Hn is the impulse response, okay? Hn is the impulse response. Okay? So the convolution is there, okay? So actually here, the only a sequence, non-periodic sequence is there. So this is a linear convolution, okay? Here you have to use the linear convolution, okay? Linear convolution. So linear convolution is not much difficult for the discrete time signal, okay? But continuous time signal, the convolution is very much difficult. But for the discrete time signal, this is not much difficult. So maybe you can calculate the linear convolution also, okay? And but here uh, you are asked, so here the yn is given, okay? Yn is given. Now you are asking to find the xn. So here yn given, hn given. Okay, you are asked to find the xn. Okay, so you can do the inverse convolution. Okay, so you have to use another method for that. Okay, I think you can understand what I'm saying. Okay, if you are given xn and hn, you can perform the linear convolution, no issue. Okay, but you are not given xn, you are given yn and hn. Okay, then you are asked to find the xn. Okay, for that one, you need to convert, you need to use the convolution property. Okay, so this property you have learned related to Fourier transform. Okay, if you do a domain transformation, for example, if you convert this yn into z transform, yz is equal to xn, also you can convert z domain, that is xz, and hn also you can convert that, let's say that is hz, okay? Then this convolution will become a multiplication. Now you can calculate xz by taking the ratio of yz and hz, okay? So you have to use this method. You have to use this method, okay? So in this question, you are given yz and you are asked to find the hz, okay? So maybe sometime you will be given xn and hn, okay? And still you can convert. You can do that, okay? So what you need to do, you can convert xn into xz, hn into hz, then you can get the multiplication, then you can calculate the yz, and if you get the inverse z transform, okay, that is z minus 1 of yz, you can calculate the uh, signal. You can get the yn, okay? So same manner, so now you are given yz, now you are given yz and hz, no? Okay. Actually, yz is directly given, but hz is not given. So here the sample is there, okay? So what is the hn actually? What is the hn? This is u, okay? Here the u n minus 2 minus delta n. So what is this actually? Okay. So you know that, okay? So hn is given. Hn is un minus un minus 2 minus delta n. Okay. When you making minus delta n අඩුපාඩු. ඉස්සෙල්ලා බලන්න මේක මොකක්ද කියලා. un කියන්නේ මොකක්ද? What is un? So it's starting from 0 like this. No? Up to infinity. Okay. Then n minus 2 means n minus 2 means n minus 2 means this is shifting up to 2. Okay. So 0, 1, 2. When it's starting from here, it is going like this. Okay. Okay. And if you get the subtraction, okay. So these two sample will be there, and this is 0, 1, 2. So from 2 it will be 1. This one also 1. This one also 1. These are also 1. So 1 divide 1 minus 1, it will be 0. So you will have like this one and this one, 0 and 1. But again, minus delta n is there. Minus delta n is there. Okay, minus delta n means this one, no? Only this one. So this one also will be there. If you minus delta n means this is the delta n, no? Okay. So if you subtract this one from delta n, so you will have only this sample. Okay. So your hn will be, this one is 0 and this one will be 1. 0 to 1. This will be your hn. Okay. Then how to calculate the hz? So very easily you can calculate the hz. Okay. Hn is nothing but 0, 1. This is the 0th sample. This is the first sample. Okay. So you know the hz, that is minus infinity to plus infinity. Actually, minus infinity to plus infinity here, not there. So it will be 0 to 1 xn, sorry, hn z minus n. Okay. So you have to expand this. Once you expand this, what happened? Okay. What happened? So 0 to 1. So it will be h0 z0 plus h1 z minus 1. So this will be hz, no? So this will be 0 because h0 is 0. So this will be 0 and hz will be z minus 1. This is hz. Okay. So if you want to find xz, xz is yz divided by hz, no? Yz divided by sz, this one. Okay. So yz is this one. 2z minus 9, z5, z5, z4. And this should be divided by z minus 1. This should be divided by z minus 1. Okay. And z minus 1 will go up, no? So xz will be, xz will be z minus 9 divided by z5, z minus 4, z minus 5. Okay. So in this way you can write. Okay. Okay. Now what you need to do, you need to find the inverse of xz. Inverse is a transform of xz. Okay. So that you can find the xn. Okay. So that you can find the xn. So what you need to do? Okay. So you need to find the inverse Z transform. For that one, actually, you are given hint, this hint. Okay, so you can use that hint in the same manner. Okay, so this can be written as, okay, for simplicity. Okay, there. So maybe there may be a, I can't remember now. Okay, so it may be a what is called the printing mistake, or maybe there is a method also. It may be not a printing mistake. Okay. Anyway, for simplicity, I will take this as Z. Okay. Don't worry. I will take this as Z. Okay. මේක මම ඉසෙට් විදිහටම ගන්නම්. හරි. එතකොට මට ගන්න හදන්න ලේසි නැත්තම් පොඩියක් අමාරු වෙනවා. අප පොත බලන්න ඕනේ. හරි. මේක මම දැන් ඉසෙට් විදිහට ගත්තොත් එහෙනම් මම මොකට නිකන් ප්‍රොසීඩ් එක කියන්න. හරි. මම මෙයා ඉසෙට් කියලා හිතනවා. එහෙනම් මෙතන මේ ඉසෙට් කැපෙනවා. හරි. එතකොට yes, this kind of question will be there. And you will get 10 marks. Okay. And maybe not in this way. Okay. But these things you have to do. Okay. For example, as I told you, okay, in this side, in this question, you are given this one and this one. And you are asked to find this one. So maybe you will be given this one and this one. Then you will ask to find the HZ. Or maybe you will be given XZ and HZ. You will ask to find the YZ. So it may be like this, okay? But the same things, okay? There, okay? I think this is not much difficult, okay? You can understand what I'm doing, okay? So I will take this as Z square, okay? Then I can easily evaluate this. I will take this as Z square, okay? YZ as Z square. YZ as 2Z minus 9 Z square, Z minus 5, Z minus 4. Okay, I will take this as Z square. Okay. Then if I take it Z square, then what happened? Again, YZ divided by XZ. Sorry, YZ divided by HZ. That is XZ, no? Okay. Then I can find the XZ. So HZ is Z minus 1. So this is divided by Z minus 1. This whole part is divided by Z minus 1. Okay. So this will be go up. And again, it is cutting. Okay. So you will be having XZ as 2Z minus 9 Z minus 5 Z minus 4. Because this is Z square. This Z is going up. Then Z, this one cancelled out. So Z only there. Okay, like this. Okay. Okay. Now I can write this XZ as so here I can write this. Okay, I am using this one. 2Z square divided minus 9Z. I can write as Z. Z minus 4 plus Z minus 5. Okay. So again, this is at cancel out, no? Okay. So I will have 2 Z minus 9 as Z minus 4 plus Z minus 5. Okay. In this way, I will have, okay. Then if I apply it here, okay, if I apply here, XZ can be written as Z minus 4, okay, Z minus 4, Z minus 5, Z minus 4, plus Z minus 5, Z minus 5, Z minus 4 in this way, okay. So Z4 cancel, this one cancel, okay. So I will be having 1 Z minus 5 plus 1 Z minus 4. Okay. So this will be XZ. Okay. Okay. And how to find the, so you need to find the inverse transform. For that one, you will get, you can get Z xn. Okay. So if you see, okay, and if you see like this, okay. For example, if you consider this example, let's say that I will take this as an, okay. So xn, I will take as an, un. Then what is the answer? An, un. So you can use this one, okay. If xn is an, un, what is xz? It will be 1 minus a, because this half I will take as a z minus 1, okay. So I can write this as z, this z minus a. In this way I can write this, no? Z minus a. Okay. Um, okay. Uh, මෙතන ඉසෙට් නැතුවම තමයි ගන්න ඕන හරි. ඉසෙට් එකක් දාලා ගත්තොත් වැඩේ කචල් යනවා. ආපහු අමාරු වෙනවා. හරි. විදියක් ඇති හදන්න හරි. මේකට මොකක් හරි ක්‍රමයක් ඇති. ඒ කියන්නේ මොනවා හරි මේ උඩින් දීලා ඇති මම මේවා. එහෙම නැත්නම් මම එක්සෑම් එකේ වෙලාවදී හරි කියන්න ඇති. හරි. මෙතන මේ ඉසෙට් තිබ්බේ නැත්නම් තමයි හරියන්නේ. මේක ලේසි වෙන්නේ. මෙතන ඉසෙට් තිබ්බේ නැත්නම් උඩ ඉසෙට් එකක් ඉතුරු වෙනවනේ. හරි. එතකොට මෙතන ඉසෙට් තිබ්බේ නැත්නම් ඒ කියන්නේ යට ඉසෙට් එකක් තිබ්බේ නැත්නම් හරි. If there is no Z, okay, I think without Z I need to get this, okay. Without this Z5, without the Z I have to get it. Then the question will be easy, okay. So if there is not a Z, Okay, so you can see that you will have his z here. Okay, not here. You will have z here. Okay. No, if there is not z, you will have like this. Okay, you will have 1 over z minus 5 plus 1 over z minus 4. No, so to have a z actually here, you need to have a z minus 1. Okay, z minus 1. Here you have z minus 1. Okay, so here also you will be having z minus 1. Here also you will be having z minus 1. This will go up. Okay, so it will be, so in the same way, it will be xz will be z, z minus 5 plus z, z minus 4. Okay, so you can see that this is identical to this one. Okay, so so this one Fourier transform is this one. Okay, so what is the Fourier? Sorry, Z transform is this one. Then inverse Z transform of this one will be in this form, no? Okay, so here you can get Xn as, you can get Xn as, so here actually A is 5, no? So it is just like 5n un plus here it is A is like 4. So you will have 4n un. Okay, so you can get the Xn like this easy. Okay, you can get the Xn value like this. Okay, maybe if this is Z5, maybe there is a way. Okay, there is a way. Okay, but I need to think. Okay, so I get this as Z minus 1. So I can use directly this one. Okay, what I want to tell you is that if you are asked to find this kind of inverse Z transform, okay, so this way you can directly get it. Okay, so don't worry. Okay, you can directly get it. You will be given a way to directly get a inverse Z transform. Okay, so don't worry. තේරුණානේ කියප එක නේ මම මෙතන z එක z minus 1 කරගත්තේ මේක ලේසි වෙන්න. හරි නැත්නම් මේක ආපහු මට පොඩ්ඩක් හිතන්න වෙනවා ආපහු. හරි සමහරවිට මේ පොතක් බලන්න වෙනවා. හරි මෙතන z 5ක් ඒ කියන්නේ අන්තිමට කැපිලා මෙතන z 4ක් ඉතුරු වෙනවනේ. හරි ඒකෙන් තමයි මෙතන z minus 1 ගත්තා. එතකොට ඒක උඩට යනවා. හරි උඩට ගියපම මට ඩිරෙක්ට්ලි ගන්න පුළුවන්. දැන් මේ වගේ එකක z transform එක ඩිරෙක්ට්ලි ගත්ත හැකි ඉන්වර්ස් Z transform එක මෙහෙම කියලානේ. මොකද මේ වගේ එක Z transform එක මේක. එහෙනම් මේකේ ඉන්වර්ස් Z transform එක මේක එනවා. දැන් ඔකටට එක්සෑම් එකට දෙන එකෙත් ඒ වගේ ඩිරෙක්ට්ලි ගන්න පුළුවන් එකක් දෙන්න. හරි? හරි. එතකොට මෙන්න මේ වගේ ගාණක් සමහරට එයෝ කට්ටියට. Okay, so you will be having this kind of questions. Okay, but maybe some plus minus changes. Okay, with minor changes. Okay, so I hope you get it. Okay, so do you have any problem with this question? මේක මොකක්ද ප්‍රශ්නයක් තියෙනවද? දැන් මෙන්න මේ දීලා තියෙන එකෙන් සමහර විට මේකට ගන්න පුළුවන් ඇති. හරි. ඒ කියන්නේ මෙන්න මේ වගේ එකක්. ඕකේ. මෙන්න මේ වගේ එකක් ගත්තාම මෙන්න මේ වගේ එකක් එනවා ඇති. මෙතන. හරි. එතකොට මෙන්න මේ කෑල්ලෙන් මෙයාව ගන්න පුළුවන් ඇති ඩිරෙක්ට්. හරි. ඒක චුට්ටක් බලන්න හදලා. මෙන්න මේ දීලා තියෙන එකෙන් මෙයාව ඩිරෙක්ට්ලි ඉවලුවේට් කරන්න පුළුවන් ඇති මේ විදිහට හදාගෙන. හරි. මේක චුට්ටක් බලන්න. ඕකේ. ඒක චුට්ටක් බලන්න එහෙම පුළුවන් ඇති. මම හිතන්නේ එහෙම තමයි මේක හදන්න තියෙන්නේ. මම දැන් මේ කැලේ ඉවලුවේට් කරපු නැති හින්දා තමයි මේක Z-1 කියලා ගත්තේ. හරි. මේක පැටලුන්නේ නැහැ නේද මම කරපු එකේ. Do you have any confusion what I have done here? මෙතන මොකක් හරි ප්‍රශ්නයක් තියෙනවද ඔය කට්ටියට? If you have any problem you can ask me, okay? So this kind of question you will get and you can get 10 marks for that one, okay? Around 10 marks you will be having 10 marks. Okay? මේවා හැම ඩිරෙක්ට් හරි මේවා මේ පොතේ තියෙනවා ඒකයි මම කරේ නැත්තේ මේක මම නිකන් හදලා හිතලා දාපු ගානක් ඕකේ එතකොට මේ වගේ ගානක්ම මම දාලා තියෙනවා මේකටත් හරි හරිනේ so if you have any problem you can ask me okay so don't get confused okay so So maybe, so here the full questions is there. Okay. So here you are going to evaluate this using Z transform properties. Okay. Uh, because we have time to cover these transform properties in past previous year, but this year this semester we don't have much time. There are much holidays. Okay. So we can't complete the Z transform properties actually. Okay. So that is why I am not putting the Z transform properties in this uh, end paper. Okay. So you can do this without the properties. Okay. So you have to use that basic definition of the Z transform. Then you can calculate. Okay. Okay. I hope you get it. Okay. So I'm not going to do DFT uh, questions. Okay, so I think it is not much difficult. Okay, so you can do this kind of question very easily. Okay, so you are asked to 8-point DFT. Okay, so you have to do a calculation. So actually you are asked to use the FFT. Okay, so using FFT you can easily find this one. Okay, but if you ask to find 8-point DFT, it is somewhat difficult. Okay. uh, so here what you need to do is, okay, so I will again tell you, you will not have in the FFT algorithm, okay? For the exam, you will be not having the FFT algorithm. So you no need to go through this FFT algorithm. Decimation in time, decimation in frequency, you no need to go through these algorithms, okay? So but you will be asked to calculate the endpoint DFT directly, okay? So 8-point DFT may be directly. It is not 8-point, okay? Because if it is 8-point, you have to do a calculation. uh, much calculation. So you will be asked around 4 points, 3 points, DFT like this. Okay. So anyway, if you want to recap, okay, if I take this question, okay, if I take this question, so if you want to calculate the 8-point DFT, no problem. You know the identity, xk is equal to uh, sigma n from 0 to L minus 1. Maybe you can remember this, okay? L minus 1, xn e to the power minus j 25 divided by n kn. This is the identity you need to use, okay? So maybe you can remember that this one also written as a matrix. So it is defined as WNKN, okay? So it will be e to the power minus j 25 n kn. Okay, so this is omega n actually. This is omega n. Okay, so if you ask to find, for example, 4-point DFT, okay, if you ask to find the 4-point or 8-point DFT, that means this n is 8. Okay, n is 8. Okay, so k will be 0, 1, 2, 3 up to n minus 1. So it will be 7. So k will be 7. Okay, so if you are going to develop a matrix, okay, so you can develop a matrix, this W and K n matrix, okay, W and K n matrix. So this direction K values are there, this direction N values are there. Okay, so N also will be from 0 to N minus 1, 0 to N minus 1. Okay, because sometime L may be not N. Okay, L, the length of the sequence. Okay, length of the sequence. L is the length of the sequence, given sequence. Okay, for example, if you consider this one, so it is 1, 2, 3, 4, 5, 6, 7, 8. So L is 8. Okay, here the sequence length is, this is the sequence length. Okay, so in this question, L is also 8, and you are asked to find the number of 8. 8 n is 8. That means you are asked to find the 8 sample. Okay, here you are asked to find the sample. This n is the number of samples. Number of samples. So always number of samples should be greater than or equal to n. If it is not equal, what you need to do? So you need to add to zeros, no? End of the sequence. So that is referred as zero padding. I think we have done these questions, okay? Zero padding. So it is not much difficult. So n is again 0 to n minus 1, okay? So here, the k will be 0 in this direction. So w 0, that means e to the power 0. So you will have 1 until n minus 1. And in this way, first n is 0. In this way, n is 0. So you will have again 1, 1, 1, 1. Okay. And from here, you will be having some values. Okay. So you can calculate that value by putting k and n value. K and n value, k and, sorry, method, k n. Simple n also there, k and n value. By putting k and n value, you can generate this matrix. Okay. I will show it. Okay. So in this direction, in this questions, the xn is given 0, half, 0, half, so on. Okay, I can't remember up to 8 numbers. Okay, so you are asked to calculate first x0, x1, likewise up to xk. So these are the frequency samples. Okay, these are the frequency domain samples. Frequency samples. Okay, these are time samples. Now we convert this time sample into frequency sample using DFT. Okay, so that is the DFT. That is why we are using DFT. Convert time sample into frequency sample. But if you apply Fourier transform, what happens? So it will convert this time sample into frequency, omega. So this omega will not be a discrete value, it will be a continuous. So again, if you apply direct Fourier transform, okay, so you will get a continuous time, continuous frequency signal, okay, frequency spectrum, but not samples. But here you can get the frequency samples, okay. So DFT is the version, the sample version of FT. DFT is the sample version of FT, okay. So you can calculate x0. So how to calculate? So you can use this identity or matrix, no problem. If you use this identity, xn e to the power minus j25n kn. So here k is 0. So this will be 0 and it will be 1. No, e to the power 1. So you have to only expand this xn up to L minus 1. So you will have x0 plus x1 plus x2 plus so on up to x7. Okay. So you have to add these values. Half, 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 4 half. Okay. So you will be having 2. Okay. In the same manner, you have to calculate x1. Now k is 1. K is 1. So this e to the power terms will be there. So you will have x0 e to the power minus j 25, n is 8, k is 1, n is here 0. No? x1 e to the power minus j 25, n is 8, k is 1, n is 1 in this time. Now x2 e to the power minus j 25, n is 8, k is 1, j is, n is, simple n is 2. So that you can find. Okay. So in this way, you can calculate the number of samples. Okay. Number of frequency samples. Required number of frequency samples. Okay. So I think that is not much difficult. Okay. It is not much difficult. So maybe you can do some example here. Discrete Fourier transform, that is okay. So, this seventh chapter. Okay. So this is the DFT and IDFT. Okay, this is the DFT and IDFT. Maybe you can say that in IDFT you no need to do integration. No, again you have to do some addition like this. Okay, so IDFT also very easily you can calculate. Okay, IDFT also very easily you can calculate. Actually, if you use IDFT, if you are given very small sample, maybe around 4 points like this, Okay, so you can use DFT and IDFT to calculate these values. Okay, for example, using Z transform, we have calculated previous, this equation. Okay, so this equation is again valid for DFT. Okay, so xk is equal to yk divided by hk. Okay, in this way you can calculate the xk value. Okay, if the xk value is calculated by applying again IDFT, you can calculate xn. Okay, so this inverse Fourier transform is also you need to see. Okay, because it is somewhat easy. Rather using Z transform and FT, if you use the inverse DFT, it will be easy. Okay, so maybe you will get some questions. Okay, in this way. Okay, so for example, you can easily find this, verify this result. Okay, using power series. This is also power series. Okay, and this is the matrix. This is the matrix. You can see that this is K, that is from 0 to n minus 1. This is n. Again, it is 0 to n minus 1. Okay, so this is here in this way, K is 0. In this direction, sorry, in this direction, n is 0. In this direction, K is 0. So this terms and this terms will be 1. Again, you will be having some values for here. Okay, so it is, you can calculate using these values, these omega n. You can calculate using this. For example, here this is omega n 1. Okay, omega n 1. Omega n 1 means J25 divided by n 1. Okay, so that is this one. This one is omega n square. So that means you have to get the square of this. Okay, so n is given. For example, if the n is 8, you can calculate this one using a Euler formula or maybe calculator. This will be a complex number. Then you have to get the square. Okay. Then omega 3. Here omega 3. Again, you can get the square. Okay. So once you calculate some values, you can see that these are repeating again. So it is not much difficult. Using the matrix, you can easily calculate this omega n values. Okay. These values. Okay. So you can see that there is a symmetric property. Okay, there are some same parts are there. Okay, for example, this is for omega 4. Okay, maybe you can try this one. Okay, this is not much difficult. Okay, you can try this one. So you can see that the repeating. Okay, so only you have to calculate some. This is not omega, actually W. Okay, so very small W values. Okay, a small number of W values. Others are repeating. Okay. This is a circular convolution. I think you no need to focus on this one, circular convolution. But I think maybe previous, if in this exam, in this paper, maybe circular convolution questions also maybe have given. I can't remember exactly. Okay. But here in this time, no circular convolution. But you can use linear convolution. Okay, it is not much difficult. It is very easy. I think I have uploaded one session related with linear convolution and as well as circular convolution. Both are not much difficult, okay? But in continuous time domain, the convolution is very difficult because you need to do an integration and also you need to check the regions. But here only you need to add. Take the samples and add, okay? So maybe so you can do maybe try to do this kind of question, okay? So this is not much difficult. I think you can do this by yourself. Okay. This kind of question, try to do. Okay. Okay. So then that is question 3. Okay. So question 3 will be based on Z transform and discrete Fourier transform. Okay. And I will go to the question 4. Question 4 is directly related with the whole question is related with design of digital filter design. Actually, FIR filter design. FIR filter design using window method. Okay. So window method is not much difficult. Okay. In window methods, normally you will be given a frequency response of the filter. Okay. H omega. Normally, frequency response will be given H omega. Okay. So this is the frequency response. Using the frequency response, you should be able to identify whether the filter is low pass filter, band pass filter, or high pass filter. I think it is not difficult. Okay. It is not difficult. Okay. So what you need to see the regions only. Okay. Then maybe also band stop filter. Band stop filter. Okay. So these 4 types of filter you should be able to identify by looking at the um, uh, frequency response. Okay. Okay. So you will be given this one. Then what you need to do? You need to calculate the HN. Okay. The impulse response. That means the time domain response. This is the frequency transfer function, frequency domain response. Then you need to calculate the time domain. So frequency domain into time domain, what you need to do? You need to apply inverse Fourier transform. So inverse Fourier transform is if the H omega is given, you need to multiply it by j omega n, and you need to integrate within using d omega. Okay, and maybe as I can remember, you have to get this one 1/2 5. Okay, so this will be HM, this HN. Okay, so using this integration, you have to find the HN. Okay, then you will be given a window. Okay, these are the window normally. Okay, so the rectangular window. So this kind of window. Okay, for example, if you consider this window. Okay, so this M is the number of filters we use. Okay, so you will be given it 5-tap filter, 6-tap filter like this. Okay, so this M value is that one. So N is again, so if it is 5-tap, N is from 0 to 4. That means 0 to M minus 1. Okay, so N is from 0 to 4. So you have to use this 0 to 4. So you can calculate this window value. Okay, window value. Let's say that is omega n. Okay, so for example, uh, if you are asked to calculate, if you are asked to use this one triangular window, and if the m is 5, okay, how you can calculate omega n? So first omega 0. This is omega. So if the m is 5, n also will be 0 to 4, no? Then you have to calculate omega 0, omega 1, omega 2. Sorry, this is W, okay? I'm sorry, this is W, okay? W0, W1, W2, W3, W4, okay? These window values you need to calculate, okay? So you can calculate it because these windows are given, okay? For example, omega 0. That means this, sorry, W0, that means this N is 0. So M is 5. 5 minus 1, 5 minus 1, it is 4. 4 divided by 2, it is 2. 2 into 2, it is 4. Okay, again 4 divided by 5 minus 1, that is 4. 4 into 4, it will be 1. So 1 minus 1, it will be 0. So omega 0 will be 0. In the same manner, you can calculate M1. So here N is 1, M is 5. So you can calculate N1 value, W1 value, W2, that means N is 2. So here you can apply 2. Okay. You can calculate N2. Likewise, you can calculate this. Okay. Then what you need to do? You need to multiply. Uh, Hn you find, then what you need to do? Hn you need to multiply it by the omega n. Then you can calculate the appropriate Hn value. These are the FIR filter Hn value. So that is what you need to do. Okay. So I think it is not much difficult. I hope you could do this also. Example. මම හිතන්නේ මම මෙන්න මේ වගේ එකක් තමයි අර මේක කරලා තියෙන්නේ. හරි. ඔය කට්ටිය පොඩ්ඩක් මෙන්න මේ වගේ එකක් try කරලා බලන්න. හරි. මේ field එක මොකක්ද මේක? What is this filter type? This is the same way, okay? මේක ඉන්නේ band fast filter එකක්. band fast filter එකක් කොහොමද මේක කියන්නේ? හරි. දැන් මේක ඇන්දොත් එහෙම ඔය කට්ටිය HD ඔමෙගා ඇන්දොත් එහෙම ඔක කොහොමද දෙන්නේ? මේක ideal. හරි. මේක ideal field response එකක් මේ දීලා තියෙන්නේ. actual එකක් නෙවෙයි ideal එක. හරි. අපි දැන් අර microwave වලට එහෙම දුන්නේ. microwave වල අපි ඉගෙන ගත්තේ actual filter response. Okay, so we are given actual filter response in microwave communication. So for that one, it is not like this. Okay, we are not going to use this kind of things. Okay, but here this is ideal one. Okay, so you can see that omega, this is omega. Okay, omega less than 5/6. Let's say that 0 to 5/6. It will be 1. Okay, then 5/6 to 5/3. Again, it is 0. 5/6 to 5/3, 0. Again, 5/3 to 5, again 1. Like this. Okay. So it is like this. And if you consider this one, this is also like this. What is the filter type? Is this band fast filter or band stop filter? Can anyone tell? Is this a band fast filter or band stop filter? Just try to verify this by yourself. Okay, it is not difficult. Okay? So I think these are very simple things. You have know the filter response. Okay, ideal filter response, you know. Okay, so this is not much difficult. Is this band fast or band stop? It's a band stop, no? This is a band stop filter. Okay. Yeah, it is given. Band stop filter. Okay. So you need to verify this by looking at this. Okay. So you can see that what you need to do, you need to get the HN. So using the inverse FT. So very easily you can do. It is same as this one. Okay. So I have done this question. Okay, same way you have. But here you are asked to use Hanning or Blackman mean. Okay. So that one you need to use that expression to calculate Wn value. That is the only difference. Okay. So I think that will be also very easy question. Okay. So I hope I have given you some steps and clue to do some questions. Okay. So try to do this paper by yourself and also try to do the examples I have highlighted. Okay. So I will upload this lecture to the LMS. If you have any problem, you can ask. We will wind up, okay? Before winding up, if you have any question, you can ask. If you don't have question, you can leave, okay? If you, we will wind up. If you have problem, you can ask. If you don't have, you can leave. I will upload the session. Yeah, I will upload, okay? I will upload the session. I will upload the session. I think it is sufficient. Okay. If you refer the last paper with the understanding, okay? ඒක නිකන් ලියාගෙන ආවට බැරි වෙයි ලියන්න. ඔයා හරියට ඒක කරොත් understand එකක් ඇතුවට ඔය කට්ටියට මේ paper එකක් ලියා ගන්න පුළුවන්. ඒ කියන්නේ ඒකෙත් පාවිච්චි කරලා තියෙන basic theory. Basic theory පාවිච්චි කරලා ප්‍රශ්න උත්තර ලියලා තියෙන්නේ. මේකෙත් basic මේවා පාවිච්චි කරන්න. Basic එක පාවිච්චි කරලා පොඩ්ඩක් හිතලා උත්තර ලියන්න තියෙනවා. එතකොට ඔයාට මේක හරියට සමහරට වෙන්න පුළුවන්. හරි zero poles එච්චර අමාරු නෑනේ කොල්ල හොයන එක. හරි. Maybe as I can remember, zero poles you need to find, okay? In the HZ. ඒ කියන්නේ impulse response එකේ zero poles හොයන්න තියෙනවා කට්ටියට. මම මතකයි. හරි, okay, thank you.